So the warm-up question says, Cedric pulls at a leftward angle to slow down a wagon rolling to the right. Is Cedric doing work? And then if yes, is his work positive or negative? If no, why is this not work? So this is a situation that looks something like this. This wagon, we've added some details here, but it says, Michelle hopped in her wagon atop a hill and started rolling down and to the right. Her father, Cedric, caught up to her at the bottom and grabbed the handle, pulling it leftward to slow her down. So basically this wagon she's sitting in is moving right, but he's pulling to the left. But he's pulling at an angle. Okay, and yes, this is going to be work. Okay, he is doing work on the wagon. And because his force is opposite the direction of the wagon's displacement, or at least a portion of it is, we talked about how the direction of force and displacement, if they were opposite, that was negative work. We also said negative work is going to occur anytime there's energy being lost. And since he's slowing it down, the wagon is losing some of its energy. And so this would be an example of negative work. But it's also an example of a force applied at an angle, which we looked at last week as well, so or on Thursday. So let's go ahead and again, these are the answers to that warm-up question. Please make sure you have answered those. And again, this is what I was referring back to. Whenever you have that force at an angle, you're going to be multiplying FD times cosine theta, because only a portion of his force does work, and that portion is the part that's parallel to the displacement. Again, if it's parallel and in the same direction, then that's positive work. But if it's parallel in an opposite direction, where one is left and one is right, or one is up and one is down, or whatever those directions might be, then you're going to have an example of negative work. So here is another calculation problem to take a look at. Be a good one to copy down if you want to have an example in your notes. It says, a 2-kilogram ball initially moving at 3 meters per second comes to a stop over a frictional surface as shown. If the force of friction is negative 8 newtons and the ball comes to a stop over a distance of 1.8 meters, what is the work done by friction? So it doesn't have to be a person doing work. Work can be done by friction. Work can be done by gravity. Work can be done by any force. It doesn't have to be an applied force from a person. It could be a force of friction. And you're going to solve it in the same way. Force times displacement times cosine of the angle. But in this case, it's just parallel. There's not anything being applied at some angle other than along the surface. So we don't really have to worry about that. What we do need to do is multiply the force by the displacement. The force is negative 8 because friction always acts in the direction opposite the displacement. The displacement's a positive 1.2. And so our work being done, when you multiply those, is negative 9.6 joules. Okay, and so again, this is an example of negative work, which makes sense because we know that the force and displacement are in opposite directions. We also know that it's causing the ball to come to a stop, so it's losing energy. So either way, we've talked about those examples of negative work. And again, that's why it's negative. Frictional force is opposite the motion. It causes the ball to lose energy. Or you can say that the force is opposite the direction of the displacement, and that was the other criteria that we used. And you can see that mathematically right here because you're multiplying a negative times a positive. You're always going to get a negative number if your signs are opposite. Questions about this one? All right. Graphically speaking, this is that same problem, that negative 8 newtons applied over that distance of 1.2 meters, and we see it represented here in a graph. Okay, it says, same problem actually, what is the work done by friction? So you could see the same information that's been presented in this question shown on a force displacement graph, like this one, where your force is plotted on your y-axis and your displacement is plotted on your x-axis. And if you see a graph that looks like this one, the area of this graph, length times width, ends up being force times displacement, which is the equation for work. So if you have a force displacement graph, the area of your graph will be equal to the work being done. Okay, and so if you ever see this type of graph, find the area and you will have the work, and we get the exact same answer when we do length times width for this rectangle as we got just reading the word problem itself. Okay, so if you see a force displacement graph, find the area. The area will represent the work being done. For a rectangle, that's length times width. If it was a triangle, you would need to do 1/2 base times height. Or if you have a shape like this, now you have a series of triangles and rectangles that you have to find the area of each of them and add them together. So this one says a horizontal force pulls an object across a horizontal floor. The graph at the right describes the force and displacement. Find the work. So again, if you have a force displacement graph, find the area. It will be equal to your work. Break it into regular shapes. Triangles like this one, you'll use 1/2 base times height. And you're going to use the numbering on the axes. So the base here is 1, the height is 10. Half of that is going to be 5 joules for that first red triangle. Then we have this rectangle here. Again, for a rectangle, that's just length times width. Use the numbering again. Across the bottom, the length is 2, because it's from 1 to 3, and then times 20. And so 2 times 20 is 20 joules. Or sorry, 2 times 10, sorry, is 20 joules. Again, here we have this triangle sitting on top of another rectangle down here. You can do these in either order. But again, 1/2 base times height. My base here is 1. My height is from 10 to 30. That's a height of 20. 1/2 of 20 is 10. And then, of course, that little yellow rectangle underneath it, length times width. Get all those values and add them together. Okay, I don't know you'll have one this complicated, but if you do, you can do it. You just need to break it into regular shapes. When you add them all together, you get 45 joules, and so in this particular graph, the total work being done that's represented by that graph would be 45 joules. It is the area under the curve or line in this case. So again, if you have a force displacement graph, your area will represent the work being done. All right. You can also have work being done against gravity. I mentioned that a second ago. Gravity can do work, or you can do work against gravity. This one says, a 78-kilogram man climbs 3 meters up a flight of stairs. How much work does he do against gravity? Anytime you are climbing or lifting something, in this case you're lifting your own body upstairs, but lifting like a box off the floor. The force that you have to apply in order to climb stairs or to lift something is equal to the weight of the object, in this case, his weight. Okay, and so if you climb stairs, the force that you're applying has to be equal to your weight, because the force acting on you is gravity, and that's what you're working against, and so you would need to find Fg. The force here will be his weight. Fg would be equal to Fn. Again, if you think of the forces acting here, and so you would take his mass, 78, you'd multiply it by gravity, 9.8, and then his weight is 764.4 newtons. That is the amount of force he would have to apply every time he's taking a step. Okay, and so he's pressing down, or his weight is pressing down, and then the floor is pressing up on him. But that would be the force you would use for lifting or climbing, is the weight of the object. Okay, and so we can use this to find work. Okay, if we know the force and we know the distance, 3 meters up, I don't really care how much distance he goes forward, because he's not working against anything there. Okay, so we're only going to look at the vertical distance, and that means we're only going to look at the vertical force, because those are parallel. So I don't really care about sideways. But again, we can do force times distance. 764.4 times 3 gives us work being done as he's climbing up against gravity as 2,293.2 joules. Questions about that? Okay. This is an important thing to add to your notes. Work is independent of the path taken, the title on this slide. What that means is that it doesn't matter whether, and you can look at this picture here, it doesn't matter whether you move this box up to the top of this ramp by lifting it straight up from the ground or by pushing it up an incline. The amount of work that these two people will do, if these boxes are identical, is the same amount of work. It doesn't matter how it gets there. If it moves from the ground to that height, the work done will be the same because it's independent of the path taken. Okay, so the same amount of work is done to lift a box as is needed to push it up a ramp, assuming that they're going from the same position to the same final position, and that's because the force each person is doing is against gravity. They're having to get the weight of this box up to a certain height. Okay, and so when you do that, you're only looking at the portions that are parallel to each other, and so you end up with the exact same amount of work to get up here. You can calculate it, or you can just memorize this, that they're going to be the same, but they will be equal to each other. While both methods require the same amount of work, lifting a box does require greater force, but it's applied over a shorter distance. Okay, whereas the girl that's pushing it, she's going to use less force because the surface of the ramp is the lifting part of it for her, but she has to push it farther. So there is a trade-off between force and distance, but they end up doing the exact same amount of work. But this is how simple machines work. There's a trade-off of force required for distance through which the force is applied. So it makes it easier to lift the box, but now you have to push it farther. Okay, but the force required is less. But the work done is the same because work is independent of the path taken. All right, this is the main thing I wanted to get to, is just doing a little bit of practice with the angles. Okay, if you want to copy this down so that you have an example with angles, we've done forces at an angle before, but now we're going to have to be able to use these forces at an angle to find work being done. Okay, it says a man applies 214 newtons of force to push a lawnmower at an angle of 38 degrees below the horizontal as shown. If he pushes the lawnmower 10.5 meters across his yard, how much work does he do on the lawnmower? And so again, we find work in the same way, but I only care about the component of his force that is parallel to the displacement. He's not going to be displacing the lawnmower up or down. It's going across. It's horizontal. So when I look at this diagonal force, I only care about the horizontal component, which could be drawn on this dotted line right here. And when I look at SOHCAHTOA, I know that that is the adjacent side. And so I would be using cosine, which we also already know because it was in our dot product equation. FD cosine theta. Well, this right here is F cosine theta. So once we get this, we just have to multiply it by the distance. Okay, you can do it all at once in one single step with that equation FD cosine theta, or you can find the component and then multiply it by the displacement. It'll give you the same answer. But this will give us the x component. His 214 Newton force multiplied by the cosine of 38 degrees would give us the x component that could be drawn on this dotted line to the right. That amount is 168.634 newtons. And so that is the only portion of his force that does work. Not all 214 newtons does work. Only 168.634 newtons does work. And so you would take that and multiply it by that 10.5. Or, as we saw last week, you could just do FD cosine theta all in one step, in which case you'd have 214 times cosine 38 times 10.5. It's the same thing. Okay, you're still going to get 1,770.7 joules. So that would be the amount of work that he does in applying that angled force to move that lawnmower 10.5 meters. Again, I know we're going kind of quick because we're trying to get caught up with everything. But you can copy this one down if you want to go back and look at it again. This is slide 33. You're welcome to make that note in your notes, and then you can go back and look at it and do it slower if you need to. Again, your other option is to just go straight to this equation. It's the same thing. Here's the 214 times the cosine 38. That's how we got that 168. You still get the same thing. Okay, so whichever way you want to do it is fine. But I want you to understand why you're using this equation, and that's why I showed it to you the other way. Okay, we're getting that component that is parallel to the displacement. Again, why is it positive? Well, he's adding energy to the lawnmower because he's pushing it and causing it to move, for one. So it is added energy. The other reason is because his force and the displacement of the lawnmower are in the same direction. A portion of his force is to the right, the lawnmower moves to the right. When they're in the same direction, you will get positive work. All right, here's a follow-up question. If the net work on the mower is 1,200 joules, find the work done by friction, and then we're going to find the force of friction. Okay, so I already know the work done by the man. I just calculated it in the last problem. It was 1,770.7 joules. If there is net work, remember the net work is the total, the sum total of the work. So it's the man plus the work done by friction. So it tells me the net is 1,200. Here's the man's work. So I know friction has to be doing negative work, which makes sense. It should. Okay, friction always acts in the opposite direction, and so if it's acting opposite the direction that he's pushing, it's opposite the displacement, it will be a negative number. And you can see that algebraically because if I isolate this, I have to subtract 1,770 from 1,200, which will give me a negative value, specifically negative 570.7 joules, and that would represent the work done by friction. Notice this question didn't give me a force of friction to calculate it with. Instead, it gave me the net, and I had the mans, and I had to find it by subtraction. Sometimes you have to do that. Okay, so make sure you pay attention to all the information you've been given. With this work done by friction, though, we can now solve for the force of friction because, again, work is still force times displacement. Okay, and so the work done by friction will equal the force of friction multiplied by the displacement of the lawnmower, which in the original question was 10.5 meters. So if I wanted to solve for the force of friction, I need to divide both sides by 10.5, and that would give me a force of friction of negative 54.35 newtons. Okay, so again, we can now solve for force of friction using the work equation if we happen to know the work done by friction. It's giving us just more formulas that we can use to solve for things in a variety of different ways. Okay, questions about this one? All right. That is the assignment that we had from Friday. So if you haven't done this yet, hopefully you did because we started it Thursday, but that needs to be taken care of. It should have already been turned in by 11:59 p.m. on Friday night.